Chapter 6 Metal Processing. Within this chapter, we have 5 topics. The first one is the extraction of metal from ore, that I will focus on the blast furnace. And the second topic is on iron and steel making. There will be 2 types of furnaces. The first one is the BOF, or basic oxygen furnace, and the second one is the electric arc furnace, or EAF. Then I will move on to metalworking process, including forging, rolling, extrusion, drawing, and sheet forming. And in terms of metal casting, there will be sand casting, die casting, and investment casting. And on the last topic, I will show you some other metal processing, such as powder metallurgy and metal joining. For the learning outcomes, by the end of this chapter, you'll be able to explain principles and then give advantages and disadvantages of each metal forming process. And next, you'll be able to select suitable metal processing based on formability and economical basis. Topic 6.1 Extraction of metal from ore. And if we look at things around us, there are components that made from metals. And all these metallic components have been through many steps of metal processing. And so the metal processing involves processing and converting of metals into usable forms. And for example, if we talk about the ferrous alloys, there are 3 main processes involved. The first one is the extraction process, that we change the metal ore into metals. And then for the ferrous alloy, we have to go through the iron and steel making, where we adjust its composition and refine the steel to obtain the steel grade that we want. And at this stage is the primary process. Then the steel have to go through the secondary process, that it has to be changed into desirable shape through either mechanical forming or casting. And by looking at the picture on your left-hand side showing the extraction process of metal from ore, that requires quite a bit of energy consumption, as you can see from the picture. But before we go through the process, I would like to mention about circular economy, because circular economy is the key to successful metal life cycle. If we're thinking about making the metal into desirable shape, as we start from the beginning, from mining process, and then we go through the refining process to make the steel or metal getting higher purity. And then we go through the primary production over here, then change the metal shape in the secondary production to the desirable shape before it get through the customer who using the product. For example, in automotives, biomedical, telecommunications, electronics application, and so on. And after use for a certain period of time, if you're not careful enough after use, the metal part will end up in the landfill that will produce the solid waste. And that we need further treatment, and maybe it's just the waste. And please be reminded that among 3 materials, metal is capable of recycling. Therefore, it's better for us to reuse the metal again or to close the loop to produce zero waste. And it is our responsibility to do so. First, try to reuse it. The second use will help to extend the metal life furthermore. Or we can choose another option to close the loop like this. The first loop is to go through the secondary production. The second loop going through hydro-process recycling, that the metal part will go through the primary production, secondary production, and then go to the customer again. And for the biggest loop is through the pyro-process recycling, that the metal part will go through the refining step, and then through the primary, secondary production before going through the customer again. So to this, we can preserve the metal resources to its best efficiency. That we can produce the metal products when first passing through the primary process and then to the secondary process to produce the final products of desirable shape. Now let's get back to the start on the metal extraction. We have 3 important raw materials, namely iron ore, coke, and limestone. These all three raw materials will be charged into the so-called blast furnace. The blast furnace will produce the molten pig iron through the casting process like this. And since the pig iron has high content of carbon, it is prone to brittle, so we have to reduce the carbon content by using the basic oxygen furnace or the BOF. Before going through the steel refining facility, and this process is called iron and steel making. And then the steel is ready for forming, either through the continuous casting process to produce products such as slabs or thin slabs, or blooms and billets. But then if we consider another shortcut to produce the steel, apart from going through the blast furnace, the iron ore and coke can be charged into the direct reduction process like this to produce the metallic iron from the iron ore, and then go through the steel production using the electric arc furnace. If we don't have the iron ore, we can use the steel recycled scrap as the raw material for the steel production by charging into the electric arc furnace or the EAF to produce the molten steel. Then the steel will be subject to refining as well before going through the forming process. As mentioned earlier, the slab, blooms and billets are the primary products that produce from the primary processing before going through the secondary processing in order to produce the final products of desirable shapes. This diagram shows the extraction process of metal from ore. So the first part of the diagram here contains the metal extraction. Then, to obtain the final product, the metal that has been extracted has to go through the iron and steel making, which is around here, and further through the forming process, as we will focus on the blast furnace for the extraction of metal. And this diagram will show the details how to do it. By far, the blast furnace is the most popular furnace used for iron extraction because it is effective and can extract the metal from ore in a large scale. The raw materials are the iron ore, coke, and lime. The coke provides heat for extraction and acts as the reducing agent, while the lime combines with impurities and forms the slag. And let's have a look on this diagram. For the extraction by blast furnace, first, the coal is dumped into large ovens where it's heated up to high temperature, and that will convert it to coke. And the coke is used as a heat source and reducing agent. And then the coke, along with the iron ore and limestone, is sent into the blast furnace into this hopper. Next, all three elements are hoisted to the top of the furnace and sprinkled in layers into the stove. And then the hot blast of air rising then melt the falling ore. Finally, the molten iron collects at the bottom and is drained out like this for further process. And then the impurities rise to the top of the molten steel. So now it's easy to be skimmed off this way. This diagram showing a blast furnace plant having materials handling, charging, tapping, and gas handling of the hot blast equipment. As we notice here for the gas handling and hot blast equipment, the cold blast coming through this direction over here and then charging into the stove. Then the hot air rising as the reaction takes place, and then the hot air will come down into the gas cleaning equipment and sent through the combustion chamber over here through the arrows and coming out as the waste gas. This diagram shows the reactions taking place within the blast furnace at high temperature. And as we know that the iron ore, coke and limestones are sprinkled into the stove over here, many reactions take place down here to the bottom. Once the temperature increasing from the top around 500 Celsius down to the bottom around 1700 Celsius. And once the three raw materials enter the stove, the formation of gaseous reducing agent takes place at 600 Celsius. This is we have the carbon monoxide here. Then the slag formation takes place at 900 Celsius where calcium carbonate converted into calcium oxide. And therefore that is the suitable condition for the reduction of iron oxide at this temperature. where the carbon monoxide combined with ferrous oxide to form metal iron at this temperature of 900 Celsius. Then the slag is formed at highest temperature of 1200 Celsius. The calcium oxide combined with silica to form calcium silicate, for example. And then the impurity formation in iron takes place at 1400 Celsius, where the manganese oxide and silica combine with carbon to give manganese and silicon and carbon monoxide. And at the bottom, where the hot air is charged into the stove at 1700 Celsius, the temperature is high enough to form the gaseous reducing agent, as you can see from these reactions. Then finally, we have the molten iron down here that can be drained off for further production of pig iron. And then the slag is formed up here and can be easily skimmed off. That can be used in the cement industry for secondary use. What we obtain from the blast furnace is called the pig iron, and that will contain mainly the iron, and the minor elements are carbon, which is the most important, and nitrogen, phosphorus, silicon, manganese, and sulfur. Normally, pig iron has around 4% of carbon, and that must be cleaned and reduced before use. As mentioned earlier, that steels with high carbon content are prone to brittleness. The picture on your right hand side showing the casting of pig iron, that finally we will obtain this big lump of metal after solidify. The name pig iron obtained as it resembling the piglet, as you can see from this sketch. In the 18th century, there was an old method of placing small blocks in the crude iron into molds in sand bed, fed from the common runner. The block of iron were called the suckling piglet, and the runner was called the pig. Since then, the pig iron has become a widely used term. And this table shows the chemistry of the basic pig iron, the foundry pig iron, and nodular pig iron. As you can see that high carbon content of around 3.8 to 4.5%, with smaller amounts of silicon, manganese, sulfur, and phosphorus. Then with high content of carbon, the next step is to reduce the carbon content in the pig iron. In the next step, we go through iron and steel making, where we convert the molten iron from the blast furnace that has high carbon content into steel. And that is because that pig iron needs to be reduced and cleaned to make good quality steel. This can be done by using the BOF or basic oxygen furnace. As you can see from the picture over here, that the basic oxygen furnace having the steel shell outside, lining with the refractory inside. Down here is the molten iron that is blasted with oxygen via the lens that is water cooled. And up here we can charge the flux inside the furnace. The carbon in the molten metal reacts with iron oxide to form carbon monoxide, as you can see from this equation. And this reaction is the exothermic reaction that gives the heat. The process starting with charging the scrap into the furnace like this, with the addition of burnt lime and then charged with molten iron. When it's ready, the oxygen is blown inside. Once the carbon content in the steel is reduced, the molten steel is tapped out of the furnace. Finally, the remaining slag is poured out. As in the process, we add the lime. It is to combine with the iron oxide and silica to form slag, as you can see from this picture. The slag helps to reduce sulfur and phosphorus in the molten iron. The slag can be eliminated as it has lower density than the molten iron, it then floating on the top. The molten iron can be cast into pig iron or can be cast using continuous casting machine directly. Alternatively, if we don't have the iron ore, we can start from the steel scraps that can be transformed into usable steels into the market, as we use the electric arc furnace or EAF. So the EAF is used to produce carbon steels and alloy steels, such as in the form of wires, rods, or plates, that is primarily by recycling ferrous scrap. And this picture shows an example of big electric arc furnace in the action of tilting to pour the steel in the tapping process. And as you recognize here the electrodes on the top. And now let's see the real picture of the electric arc furnace in the tapping process. The scrap and ore manufactured iron units such as DRI or the direct reduced iron, pig iron carbide is melted and converted into high quality steel by using high power electric arcs that formed between the cathode and 1 for DC or 3 for AC anodes. So the scrap is by far the most important resource, accounting for about 80% of our electric arc furnace metal feedstock. And this diagram showing the details of the electric arc furnace, or the EAF, in the section view. Up here you can see the graphite electrodes that produce the arc just on the top of the molten steel. And all this is housed by the furnace shell. The molten steel will be tapped out over here through the bottom into the ladle, and this action can be done through the tilting cylinder over here. And the picture on to the right hand side showing the top view of the electric arc furnace. As you can see, the power conducting arms over here, the roof suspension beam, and the water cooled roof and water cooled cables. Once we have the high quality steel that obtained from the electric arc furnace or the BOF furnace, the molten iron can be cast through the continuous process or the concast process, as you can see from this picture. The molten iron is first cast in the copper mold and then pulled out by rollers continuously while solidifying. If we're starting the continuous process over here, once the molten iron is cast through the copper mold like this and through a series of rollers, upon cooling down or solidifying, when the temperature of the slab is low enough, it can be cut to form blooms, slabs or billets to go through further step of metal rolling. For example, the ingot or the slab can be passed through the soaking pit, passing through the blooming mill over here just to reduce the cross-section, and then going through the roughing mill is to reduce the thickness more intentionally, and finally through the finishing mill while the surface of the sheet is carefully controlled in terms of thickness and flatness, as well as the surface finish. Towards the end, the steel is subject to coiling, as you can see from coils of hot rolled steel over here that is ready for further process of cold rolling process if required. So for summary, on the continuous or concast process, the molten steel can be tapped from the bottom of the ladle into the intermediate container known as the tonnage. And now the temperature of the melt is below 1600 Celsius. Once going through the open mold consists of 4 water-cooled plates between which the hot steel slides. A solidified shell is formed during casting, and the casting temperature is around 1540 Celsius. After that, the steel is subject to cooling continuously by quenching with water along the whole series of roller stands. And finally, during continuous cooling, the steel is still hot but has solidified all the way through. When it is cut into slabs by means of oxygen lenses, the temperature is now around 1000 Celsius. Every slab is marked before it is placed on the cooling bed. And the picture on your left hand side here showing a section of the continuous casting process.